So to prove something as ambitious as Newton's law, it's going to be a fairly complex proof. So we're going to break it down into a series of steps. So we're going to have a plan that we're going to follow so that you can follow the logic more clearly. So in step one of our plan, we're going to show, right, that this key Newton's equation, F equals ma, follows actually from two simpler results. So it follows from the fact that if I look at the time derivative of the average location of my packet, right, that will have to have a certain special value. Now, in the past, in our semi-quantitative theory, you will recall that we looked at where our packet was a maximum. Now we're actually going to take the average position of our packet. And the way that average position of our packet will end up evolving in time will be such that its time derivative actually equals the average momentum of our packet divided by the mass of the particle. So in essence, this first result that we will eventually show that will lead us to Newton's law is simply the first of, basically it's the first of Hamilton's equations. The second result that we will need to show, and we will be proving these later in the future steps, I'm just saying our first step is to show we can get F equals ma provided we can prove the following. And the next step is that the time derivative of the average momentum in the system then will prove to be equal to the average of this interesting quantity, namely the derivative of the potential in the system, the potential namely that enters into the time-dependent Schrödinger equation through the Hamiltonian. It will equal the average value over all positions of this interesting derivative, which actually, of course, is just the force from that potential. So we will look at all the times and places where we find our particle, calculate the force at that location, average that up, and that will have to describe for us then the time derivative of the momentum. That is actually, of course, the second of Hamilton's equations. So first we will show that F equals ma follows from these key relations. Then in step number two, you can see that we are going to need results for how time derivatives of quantum averages behave. So there's a key theorem that describes that. It's called Ehrenfest's theorem. Ehrenfest's theorem. And Ehrenfest's theorem states that the time derivative of the average of any observable in quantum mechanics equals the following curious expression. It equals the average of a certain operator. And that operator is actually 1 over I h bar times then the commutator between the operator that allows us to compute averages of that observable and the operator that gives us the Hamiltonian of our system. Now, the first somewhat curious thing about this expression, it's not too complicated, it's just a little curious, is that we're now talking about the average of a quantum operator. That seems a little bit abstract, right? Where so far we're only really been talking about averages of observables. Now, the average of a quantum operator is really just a shorthand notation. It just means the following. We simply follow the same mathematical form for computing averages of observables and then just apply it to any generic quantum operator. So by this expression, it's just a shorthand notation. It's literally just defined as a shorthand notation for this famous inner product of psi with the corresponding operator acting on, so here's my operator, acting then on my current wave function for my system. Now, the other curious thing about this expression is that here I've defined a particular operator through this bracket. This bracket represents what's called a commutator. So there's a general definition for a commutator. So if I had any two operators, I form this bracket with the comma and the square brackets. It's called the commutator. This is an operator, so it's some mathematical operation that you would apply to some wave function or any function in general as a general mathematical operator. And the action of this operator, the result that it gives you, is defined then in the following way. First, we would apply the b operator to our function. So I'll write b first, whatever our function might be. Then, after we get the result of that, we would then apply the A operator. Now that's the first piece of the definition of the commutator. Then what we do is we subtract from that the action done in the reversed order, where we would first apply the operator A to our function, whatever might be over here, and then apply the operator B. And it's that final subtraction of these two processes carried out in reverse order that defines the commutator for us. So this is the content then of Ehrenfest's theorem. Once we have this general theorem that tells us how the time derivative of the average of any operator behaves, it'll be a very handy general theorem, useful for all sorts of different things. Then, finally, in step 3, we will come back and apply this general result. We will apply it then, Ehrenfest's theorem, to the averages of position and averages of momentum. And of course then, with a little luck, that will then actually spit back out for us the key results that we need to prove Newton's laws. So that's the basic plan of attack. We will now take these one step at a time.